Okay, on to our third and final lecture on the Laurent series and residue theorem. Um, so last time what we did was last couple of lectures we talked about Laurent series and how that leads to something called the residue theorem, and we just established the residue theorem last time. So in this page I'm just summarizing what the residue theorem was. So what you have, so what you're trying to do is you're trying to do a contour integral around a closed loop C, and you have these sorts of conditions. So F is analytic except at a finite number of points Z1 up to Zn, which are inside C, right? So you got these n different problem points which are inside C, which are given by this over here. And then what the residue theorem tells you is that if you do this calculation, then it's just going to be 2 pi I times the sum of the residues of each of these points in relation to F, right? So that's what it's saying. So all you really need to do is you need to calculate the residues at each of the problem points. And what is our formula for the residue? Well, if it's a kth order pole, we have a formula for the residue, and it's given by this thing over here. So if Z0 is a kth order pole, that means that when you do this calculation, you get an analytic function, so you can actually take derivatives and so on and so forth. And then the formula that we established last time was given by this thing over here. Okay, so what I want to do in this lecture is do a bunch of examples related to the residue theorem and show you its power. Okay, so the first example, let's look at this problem here. So we are given a function 7 over z cubed minus iz. It's a complex valued function, and we are asked to do a contour integral around this contour where the modulus of z equals half. That means that the distance to the origin is a half, so that's just simply a circle of radius a half. Okay, so how do we need to tackle this? So we need to know the residues of this function here, right? So what you need to do first is to find the poles of the function and then calculate the residues at that point. So poles of the function occur when this loses analyticity, and I mean basically from our context, it's just whenever you're dividing by something which is a zero. So they occur when z cubed minus iz equals 0. So it occurs at z values which are given by this over here, and we can quickly see that z equals 0 is a point. But then what about the rest, right? So z squared minus I. So it's a second order equation, so you're going to expect two roots. So how do you find these two roots? Well, if you want to find the roots of z squared minus I equals 0, so in problems like this, it's much easier to use the polar form. So r is the modulus and theta is the argument. So this is just a representation in terms of standard polar coordinates, of course, because this is r cosine theta plus I r sine theta. And then what I see here is that z squared is equal to I. Right. Okay, so I want to express that equation in terms of the polar form, but what is I? Well, I is up here, so it has an argument of pi over 2, and it has a modulus of 1, so I can write I in this particular way. That's your R, and that's your argument. So I is equal to 1 times e to the I pi over 2. You can verify this by applying Euler's formula to this, right? That's cosine pi over 2 plus I sine pi over 2. And you should get I. Anyway, so R is equal to 1, and the angle here is equal to pi over 2. And then we have this equation z squared equals I. So if I apply that, I'm setting z equal to that. So z squared is simply that. It's r squared e to the 2I theta. That has to equal this this quantity over here. And in this equation, so in polar form, so the amplitude has to be the same. So r squared has to equal 1. That's one thing that I see here. And then the argument has to be the same, right? So r squared equals 1, this gives us r equals 1. That's it, because r is positive. And then what you're getting here is that 2 theta has to equal pi over 2, right? But the way that we do this, because actually you're expecting two solutions. So in general, because you can keep on rotating this round and round and adding factors of 2 pi, or for that matter, subtracting factors of 2 pi. So what you do is you add a plus 2 m pi, where m is any integer. So theta is something which satisfies this. So if you divide this by 2 to figure out what theta is, so theta has to equal pi over 4 plus m pi, and m is any old integer. So if m is equal to 0, you get theta equals pi over 4. If m is equal to 1, you get theta equals 5 pi over 4. If m is equal to 2, well, what you're getting is pi over 4 plus 2 pi. So you've got pi over 4, which is along this ray, plus 2 pi means you come back to the same point. So actually you're talking about the identically the same point. So you don't have to continue any further, and even if you take negative values, you don't have to continue any further. You only get actually these two values. These are the two distinct values of theta. So when I'm looking for solutions of this, they have to have a modulus of 1, and these are the two potential values that you get, right? So e to the I 5 pi over 4 and e to the I pi over 4 are the two values that you get. They both have a modulus of 1. So what I've done here is I've drawn this line here. So that angle is pi by 4, and this angle is of course 5 pi by 4, right? Just by adding pi to this. And this distance is 1, and that distance is 1 as well, which is why there's a 1 in front of these, which I haven't actually bothered to write down. Okay, so what I've done here is I've identified the 3 different poles. We already identified that z equals 0 is a pole, and then we have these 3 poles as well. Okay, so those are the poles of this function. But what we need to do is we need to do an integral, contour integral around that. So that's a circle of radius a half. But because this is 1 unit away, that tells me that both of these guys are outside the circle, so they are not relevant to our problem at hand. So all we really care about is this point over here. So the only pole which is inside the circle is z equals 0, and it's also we know it's a first order pole because of this, right? So this is z to the power 1, z minus 0 to the power 1. It's going to be a first order pole. Okay, right. Yeah. Okay, so that's exactly what I'm arguing over here, right? So here are the 3 poles. We get them from setting each of these equal to 0. They're all first order, in fact, but because these 2 guys are outside, I don't really care. This is the one I care about. So the residue theorem tells me that in order to do this integral, I have to take 2 pi I times the residue of f at the relevant pole of interest, and I have to add them all together, but there's only one that I need to worry about. Okay, so it's just 2 pi I times the residue of f at the value 0. So I need to calculate this. Okay, and I've identified that as a first order pole. So here's my formula down here, which tells me my general formula for the residue at a kth order pole. This is from the very first slide that we had. So that's what it is for a kth order pole. But what I know is it is a first order pole. So what I need to do is I need to put in k equals 1. So when I put in k equals 1, what do I get? So k equals 1 here gives me a 0 factorial. 0 factorial is 1, so I can forget about that. And k equals 1 here tells me that I'm taking the 0th derivative, which means I'm not taking the derivative at all. And then this is the function that I get by multiplying out that pole. So what z0 is equal to 0 in this case, and k is equal to 1. So I have to multiply the function by f of z by z. So I have to multiply this by z, and that means that I'm going to get z squared minus I down here, right? So that's what I have here, right? So z over z cubed minus iz multiplied by z. Right, so that's the z minus 0 in that case, and then I need to take this limit. So I need to do this calculation. This is easy enough to do because I cancel out a factor of z, so I get this, and then now I'm perfectly able to take the limit. It's just because as z gets closer to 0, this function is perfectly well defined. So I just stick in z equals 0 here, and then I'm going to get 7 over negative I, and 1 over negative I is equal to I. So that's actually 7I that I get over here, and 7I times 2 pi I gives me 14 pi times I squared, and I squared is negative 1. So my answer is negative 14 pi. Okay, so that's how you apply the residual theorem to this. So it's actually in some ways quite easy, or not. You don't really have to do line integrals or anything like that. You've got all of these theories which actually help you, and here you're looking at z equals a half, but you could also have had some other curve which is like that. You still get the same value because you've got this powerful concept of homotoping curves as well. Anyway, so that's the application of the residue theorem to that problem. Let's look at another problem. Let C be a simple curve enclosed in the origin. Right, so in this case, you're not specified exactly what the curve is, but it's enclosed in the origin, and what you're asked to find is the value of this contour integral. And I notice immediately that there's some problem point. There's a problem point there, and that's z equals 0. Right, so it's a third order pole though, right? Because I got the power 3, so it's a third order pole at z equals 0. So let's first, before applying the residue theorem, I know I'm going to have to calculate the residue. So let me go ahead and calculate it. So here's my general formula for the residue for a kth order pole. I have a third order pole, so I have to put in k equals 3. So when I put in k equals 3, this becomes 1 over 2 factorial. K equals 3, it tells me that I have to take the second derivative. And then over here, z0 is equal to 0, of course, because my pole is at z equals 0. So what this is telling me is I have to multiply by z cubed. I have to multiply my function by z cubed. So this is what I need to do. And of course, these things cancel. And that's the whole point, right? You're going to get an analytic function here once you kind of remove that pole, essentially. So z cubes cancel. So what I need to do is I need to take the second derivative of cosine z. One derivative gives me minus sine z, another derivative gives me minus cosine z. So when I take two derivatives, I'm going to get minus cosine z, and then I need to take the limit as z goes to 0, and cosine 0 is 1, so I get minus a half in this case. So here's my residue, and once I have the residue, now I can apply the residue theorem. So the residue theorem tells me that that what I need to do is I need to take 2 pi I times the sum of the residues inside of this function, but there's only one point which is inside the function, and C is just some general curve here which encloses the origin, and so that's the only value that I need to do, and I've already calculated that. That's minus a half, and I've got this 2 pi I in front, so the answer is minus pi I. Okay, so again, so if I have something like that, and I have a general curve which encloses the point z equals 0, I'm going to get minus pi I. So quick question, if I ask you a question, what if my C did not enclose 0? What if it was something out here? The answer then would be, of course, 0, because then Cauchy's integral theorem applies, because the function is analytic in this region, right? So only point of non-analyticity is z equals 0. Okay, so it's the points, the poles which are inside the curve, which matter, and then you just apply the residue theorem, and it's pretty straightforward actually. Once you figure it out and you're comfortable with it, it's just 2 pi I times the sum of the residues. That's it. Okay, let's do a slightly different example, and this is to show that the residue theorem has Cauchy's integral theorem and Cauchy's integral formula as special cases. So in other words, this is a generalization of both of those. It's much more powerful than both of those. It incorporates both of these as well. So let's remind ourselves about Cauchy's integral theorem. So Cauchy's integral theorem. So if I have a function which is analytic inside a curve C, then the contour integral around C is equal to 0, right? So that's the integral theorem. It's as simple as that. So why is this a special case of the residue theorem? Well, if F is analytic inside C, there are no poles inside C, right? There's absolutely no poles inside C, but the residue theorem tells me that what I need to do is I need to calculate 2 pi I times the sum of the residues at each of the poles, but there are no poles, so there's no residues, right? Or another way of actually thinking about this is that the residue at a non-pole is actually going to be equal to 0, right? So there's no residues here, there's no poles here, there's no residues here, so you just get 0. So that tells us that that's equal to 0. So that tells us that Cauchy's integral theorem is incorporated, if you will, in the residue theorem. Okay, what about Cauchy's integral formula? So integral formula is something slightly different. Again, you have the same conditions for F, but now you're looking at integrating not F, but F divided by Z minus A. So you can see that you've introduced a pole here. There's a pole at Z equals A, and A is a point which is inside C, right? It has to be inside C. So if this is so, Cauchy's integral formula told us that the answer is 2 pi I times F of A. Right? That's what it told us. Now, why is this a special case of the residue theorem? Well, if I look at this term over here, and I am trying to apply the residue theorem, I first need to identify poles here. That's an analytic function. So my only pole is Z equals A, and it's a simple pole because it's this to the power 1. Right? So it's just to the power 1. It's a simple pole. That means it's a first order pole, first order singularity. Okay, so if it's a first order singularity, then when I'm trying to apply this formula. So here's my formula for a kth order singularity. So I have this k over here. But if it's a first order singularity, I'm going to get 1 minus 1, 0, right? So this tells me that I actually do not have to take the derivative at all. And over here, I have Z minus 1 to the 1 times the function I'm interested in, which is this thing over here. And you can see that these things cancel as well. What happens then, right? So K is equal to 1. This becomes 0. This tells me that I don't have to do anything. These two things cancel. So no derivative has to be taken. So I have F of Z, and I need to take the limit as Z goes to A. That's it, right? So when I take the limit as Z goes to A, I just get F of A. So the residue is just F of A. Yep, and that's it. It's F of A, and the residue theorem would tell us that this is equal to, well, 2 pi I times the sum of the residues inside, but there's only one residue inside. That's that thing over there, and we just figured out that that's F of A. So that's completely consistent. So Cauchy's integral formula is also a special case of the residue theorem. Okay, good. Now, finally, I want to do a question which is actually quite hard. So I would consider this an optional type of question, but it's interesting to look at this and try to see whether we can understand the complexity of complex numbers. So here I'm looking at a function which is like this: cosine z over e to the z minus 1, and I'm just phrasing this quite loosely. I want to investigate the nature of these contour integrals for curves in C, right? In general curves in C. So what's going to happen? Right, so we know at this point that what we need to do is we really need to have a strong understanding of the poles of the function. So the poles are the function that where this loses analyticity, and that means that I have to look where this is equal to 0, right? So I need this equal to 0, and one thing that I spot immediately is that z equals 0 is going to work, because if I put in z equals 0, it's going to be a pole. Okay, fine, but what's the order? This is not in the form, when I write e to the z minus 1, it's not in the form z minus 0 to the power something or anything like that. It's in terms of the exponential. So what order is this pole? Well, what we can kind of figure this out by using the fact that e to the z is analytic and it has a Taylor expansion, which is our standard Taylor expansion in that way. And then I'm subtracting 1 from that, right? So when I subtract the 1 from that, these ones cancel, and then I can see that there's a z in every single term that's remaining. So I can factor out a z, and then I'm going to get some stuff like this. Okay, so I'm looking for where this is equal to 0. So that's equivalent to where this is equal to 0, and you can now see that z minus 0 appears with 1 power over here. All of this stuff is kind of analytic. This part is analytic. So this is my only problem, right? So z is a first order pole because there's a power 1. Z equals 0 is a first order pole. Okay, that's good. Can I figure out the residue, right? So I need to figure out the residue. So for first order poles, the residue, I'm not going to rewrite the theorem again, but the residue is quite easy. The coefficient in front end turns up just being 1. And what you need to do here is you actually don't need to take any derivatives. You just need to take z minus z0 to the power 1 multiplied by the function of interest, and then you need to take the limit. Okay, so in this case, you can't really see how this z cancels immediately, but of course, we've already figured this out because this stuff, e to the z minus 1, we've already managed to write it in this particular form. And when you write it in that form, you can then see how the z cancels. So you're going to get cosine z over this stuff over here, and you want to take the limit as z goes to 0. When z goes to 0, cosine 0 is 1. What happens down here? Because all these terms have z's beyond this point, so you're just going to get a 1. It's 1 over 1. It's 1. Right, so the residue is 1 at this point. Okay, but are we done? Are there any other poles? Right, it's not really clear at all. Right, it turns out that there are, and the reason for that is because of the complex logarithm, which is the function which really adds to the richness of complex analysis. The fact that the logarithm, and you've got branch cuts, and you've got this 2 pi I ambiguity whenever you're defining a complex logarithm. So you have to choose a principal branch and so on. Anyway, so e to the z equals 1 means that z is equal to the log of 1. And I'm writing, when I write this down, this is the complex logarithm I'm talking about here, right? Because I'm in the complex plane. Everything's in the complex plane. So this is the complex log of 1. Now, what is the definition of the logarithm? The definition of the logarithm, complex logarithm, the real part is going to be the log of the modulus of this, and then the imaginary part is going to be the argument of this. It's going to be the argument of this, but the argument of this is 0. Right, so the argument of this is 0 because 1 is in the complex plane. It's over here, so the argument of that is 0. But actually, it could also be 2 pi. And it could also be 4 pi, right, or 6 pi, or you could go backwards. It could be negative 2 pi. So you can capture that in this term 2n pi, where n is just any integer, right? So here's your imaginary part, which is the argument of the complex number 1, and your real part is log of the modulus of the complex number 1. And here now we are talking about a real valued logarithm because this thing is now real. Right, modulus of 1 is 1. So the log, when I look at this from the real context, that just gives me a 0, and so I just get 2n pi times I, where n is in z. So I can have all of these different values of n, right? N equals 0 is certainly permissible, and n equals 0 gives me z equals 0, which is what I already know about. But I'm also getting these other factors as well, and this pole has a purely imaginary part. There's no real part to this. So there's infinitely many of these poles. So what do they look like? So they are along this, right? Because it's 2n pi I. So you have 0, 2 pi I, 4 pi I, and it just keeps going, and it goes in the negative direction as well. So you got this infinite collection of poles which lie along the imaginary axis, right? So that's kind of crazy. Then okay, so what I want to do is I'm going to have to figure out what is the residue at each one of these poles, right? So I'm going to pick a general pole. The general pole is at e to the, excuse me, 2n pi I. Sorry, at 2n pi I is where my general pole is, and I want to figure out what the residue is. In order to do that, I'm going to take this e to the z minus 1, and I'm going to do a little bit of a trick. I'm going to multiply it by this term over here and subtract 1 from it, right? So, and the reason I'm allowed to do this is because this is actually equal to 1, because that's cosine negative 2n pi, right, which is equal to cosine of 0, right, because cosine is 2 pi periodic. And then there's no sine term, because the sine term is going to be the no imaginary part, because the imaginary term is going to have sine of negative 2n pi, and that's always going to be equal to 0, because it's equal to sine of 0. So this term is 1, so there's nothing wrong in my writing this down. And why did I do that? Well, then I can combine these two terms in this particular way, and then I can do exactly what I did in the previous case, right? Earlier, I had e to the z, and I expanded that out, e to the z minus 1, and I expanded that out. Well, in this case, instead of z, I have z minus 2n pi I, and I can expand it out, and I'm going to get this, right? So I'm going to get powers of 1, powers of 2, and so on. So there's an analytic part here, and then there's a factor of 1 part which you can extract, right? So now when you look at this again, so the pole at 2n pi I corresponds to, well, this has a power of 1, and that's in the denominator here, because it's e to the z minus 1, it has a power of 1. So that means that it's a first order pole, because all of this stuff is going to be analytic when z goes to 2n pi, right? So that gets closer and closer to 1. So it's a first order pole. Every single one of these guys that you see here are first order poles. Okay. Right, so it's just a previous calculation with z replaced with z minus 2n pi I. What about the residue? Right. So let's look at the residue. Let's take n to be any general one of these guys, and what I want is I want to calculate the residue of this function at that point. So again, it's a first order pole, so we don't have to worry about the derivative, and the prefactor of 1 over 1 over 0 factorial is just 1. So what we need to do is to calculate this over here. So I take my function and I multiply it by 1 power of this, because it's a first order pole. So once again, it's not clear how this is going to cancel with that, but well, if I do the same expansion, right? I already expanded e to z minus 1, and I got 1 power of this times this stuff here. So then when I cancel that out, I just get that, right? So that cancels out with that 1 power that you get in the previous slide, and then I have something like this. Now what happens as z goes to 2n pi I, all of these things go to 0, so I just have a 1 down here, and at the top I have cosine of 2n pi I. Okay, actually I can work with this a little bit more and write it in a nicer way. It turns out that is equal to the cosh of 2n pi, so it's purely real. Right? So this is the hyperbolic cosine. And why is that true? Well, cosine of a complex number is cosine of iz plus cosine of negative iz over 2. So the cosine of 2n pi I is the cosine of I times 2n pi I plus e to the negative I times 2n pi I. And then that's what you get. But when then you got your I squared is negative 1. So this first term gives me e to the negative 2n pi. I squared is negative 1. I got another negative sign there. I got e to the 2n pi over 2. And then I look at this and I realize that this is by definition the hyperbolic cosh and the hyperbolic cosine of the factor 2n pi. Okay, so the residue is cosh 2n pi if you take a general n. So what I've done here is I've written down the residues corresponding to each of those. So here this is n equals 3, because that's 3 times n, 2 pi I. So n is equal to 3, and that gives me cosh 6 pi, right? So looking back here, right? So you get 2n pi, right? If n is equal to 3, and then they are going to get cosh 4 pi, cosh 2 pi. And here the 0, that's something we analyzed earlier. We already figured out that the residue was 1, but that's also equal to cosh 0. So this formula actually works for n equals 0 as well. Cosh of 0 is equal to 1. And then the hyperbolic cosine is an even function. So whenever you got this negative, you're going to get exactly the same as what you got for the positive, right? So the residues are given in pink over here. All right, so now this is stated in a very vague way. Evaluate the nature of this for curve C in the complex plane. So if I take a curve like this green curve that I've drawn over here, well, depending on the curve, you just have to look at the sum of the residues of all the terms which are enclosed in this, right? So if I have this green curve, I have that's inside, that's inside, that's inside, that's inside, and that one's inside. So it's 2 pi I times the sum of those terms. That's what the residue theorem tells me. It's 2 pi I times the sum of that, right? And if you have a different C, then you just need to worry about what's inside. Okay, so that example was a bit difficult. Um, and, uh, and I would say that that's optional, but that brings us to an end of the discussion of the Laurent series and the residue theorem.